Hello students, in this lecture I will talk about linear models of random signals. Let us recall the last lecture. The generalized PSD Sxz of a regular WSS process Xn can be factorized as Sxz is equal to sigma v square into Hcz into Hcz inverse, where Hcz is a causal minimum phase transfer function, Hcz inverse is an anti-causal maximum phase transfer function, and sigma v square is a constant which can be interpreted as the variance of a white noise. As a consequence, we can model a regular random process as an output of a minimum phase linear filter with white noise as input. That is, this is the white noise Vn of variance sigma square. This is input to a linear minimum phase filter of transfer function Hcz, and output is the WSS process Xn. This lecture will explore some of such models. The most elementary model is the white noise. Recall that a white noise process Vn has 0 mean because its power spectrum is flat. So, there is no DC component. It is a 0 mean and the autocorrelation function ACF is given by this Rv of m is equal to sigma v square delta m. So, delta m equal to 1 at m is equal to 0, 0 elsewhere. Now, about any non-zero mean uncorrelated process, suppose the process is not 0 mean, but it is uncorrelated. In that case, the process becomes 0 mean after the subtraction of the mean. So, therefore, any uncorrelated sequence of random variables also can be treated as white noise, because any non-zero mean uncorrelated process becomes 0 mean after the subtraction of the mean. Hence, any uncorrelated sequence, uncorrelated means that autocovariance function is delta function, that also after subtraction of mean it will become 0 mean, therefore, it will also become a white noise. So, the definition of white noise include 0 mean, but any non-zero mean uncorrelated random process also can be modeled as white noise. Now, random data with very small correlation between samples can be modeled as white noise. That means, we have suppose xn is one sample and xm is another sample, and if the covariance between them is equal to 0 for n not equal to m, then we can treat this data as white noise. Now, let us go to linear models. Spectral factorization theorem enables us to model a regular random process as an output of a minimum phase linear filter with white noise as input. That is, Vn is the input to a linear minimum phase system with transfer function Hcz, and Xn is the output, which is a WSS process. In general, now if we consider the transfer function of a causal LTI system, minimum phase LTI system, and it will have one numerator part and denominator part. So, it is a ratio of nz divided by dz. Now, this nz part we can write as summation I going from 0 to q bi z to the power minus I. This is the numerator part. Similarly, the denominator part we can write as 1 minus summation I going from 1 to p a I z to the power minus I. So, this is the general transfer function, and depending on special situations we will have different models. For example, if dz is equal to 1, if this is 1, then hz will be simply that numerator part will be there. In that case, we have all 0 moving average model. So, this is a suppose because there are q terms, I is equal to I going from 0 to q, therefore, this is a moving average of order q, MAQ model. When dz is equal to 1, that means only numerator term is there. When nz is equal to 1, then only denominator part is there. In that case, we will have poles. So, we have the all pole autoregressive. This model is known as the regressive model of order p. This is the p parameter. So, autoregressive model of order p, and this is because it has only denominator polynomial. So, that will have poles. So, this is an all pole model. Otherwise, this general model will be ARMA, autoregressive moving average in terms of parameters p and q model, ARMA PQ model. Now, in the time domain, this ARMA PQ model can be described by a linear constant coefficient difference equation. So, this is a difference equation. In terms of the difference, we are getting the equation. Therefore, x n, that is the output variable, x n is equal to summation a I x of n minus I going from 1 to p, that is the autoregressive part, plus summation b j v of n minus j going from 1 to q. So, this is the linear constant coefficient difference equation model for the ARMA PQ process. P is the number of autoregressive part, that means it tells about the autoregressive part, and it tells about the moving average part. These models are very useful. They are used data compression, signal prediction. One of the very important use of this type of model is forecasting or prediction, signal understanding, etc. In statistics, random process modeling using difference equations is known as time series analysis. In statistics, for example, in any stochastic process, stochastic finance, for example, we have time series analysis. Time series analysis means we analyze the models given by this type of difference equations. Such models has long been used in signal modeling and forecasting. So, their main purpose was earlier, it was that is signal modeling and forecasting. But nowadays, these models are used in many signal processing applications like speech recognition, etc. So, we will discuss first moving average of order q. As I have told earlier, this is a FIR filter model. So, there is the white noise is the input and x n, that is the WSS process, is the output. Difference equation will be x n is equal to summation b I v n minus I going from 0 to q. This is the MAQ process. Thus, impulse response H I is equal to b I. How many impulse responses are there? There are q plus 1, I is equal to 0, 1 up to q. And in the transform domain, frequency domain, that frequency response h omega is given by b naught plus b 1 into e to the power minus j omega plus b 2 into e to the power minus j 2 omega, and so on up to b q into e to the power minus j q omega. This is the frequency response of the FIR filter representing the MAQ process. In terms of Z transform, we will have Hz is equal to B naught plus B 1 into Z to the power minus 1 plus up to B q into Z to the power minus q. Thus, MAQ is an all 0 model, because there is only that transfer function has only the numerator term, therefore, it is an all 0 model. We know that if it is a WSS process, it is characterized by its autocorrelation function and corresponding power spectral density. We will see what is the SCF ACF autocorrelation function and PSD power spectral density of an MAQ process. The autocorrelation function Rx of M, we know that Rx of M is equal to RVM convolved with HM convolved with H of minus M. That we derived this relationship while studying that linear system, that response of a linear system to WSS input. So, there we established that output autocorrelation function is the convolution of input autocorrelation function Hm and H of minus M. Hm is the impulse response of the system. So, now I know that RVM, because it is the input is white noise, RVM is sigma v square into delta m. So, therefore, Rxm will be sigma v square delta m convolved with Hm convolved with H of minus m. But this is sigma delta function, and any function convolved you will get the same function. Therefore, this will be sigma v square Hm convolved with H of minus m. Now, use the properties of convolution. So, you know, because you are two finite duration sequence you are convolving, therefore, Rx of m will become 0 for mod of m greater than q. And if we substitute, because I know the impulse responses are the B parameters. So, if we substitute those, and this expression can be simplified to Rx of m is equal to summation j equal to 0 to q minus m of Bj into Bj plus m into sigma v square for m lying between 0 and q. So, this is the expression for autocorrelation function, and Rx of minus m is equal to Rx of m. This is the basic property of autocorrelation function of a WSS signal. Therefore, Rx of minus m is equal to Rx of m. Therefore, generalizing these two expressions, we can write Rx of m is equal to summation j going from 0 to q minus mod of m of Bj into B of j plus mod of m into sigma v square, where mod of m is less than equal to q is equal to 0 otherwise. This is the expression for the autocorrelation function of a MAQ process. Now, the power spectral density PSD is given by Sx omega, that is the PSD of x xn. Sx omega is equal to sigma v square multiplied by mod of h omega square, that is we established that relationship. Now, I know h of omega is equal to B0 plus B1 e to the power minus j omega plus up to BQ into e to the power minus j omega q. So, therefore, mod of this expression square into sigma v square. So, this is the power spectral density of an MAQ process. So, we got the autocorrelation function given by this expression and power spectral density given by this expression. Now, how do I fit an MAQ model? An FIR filter has zeros only. So, if the spectrum has some values, then MA will fit well, because if we consider suppose FIR filter, it will have 0 and those zeros will give rise to value in the spectrum. I will show an example later on. An MA model is always stationary. Why? Because FIR filter is always stable, and correspondingly Xn will be also WSS, because Hn is stable and Xn is the output of a stable system, and therefore, to a white noise this output will be also stable, and stable in the sense of random process it will be stationary. So, therefore, an MA model is always stationary, WSS in this case. Rx of m becomes 0 for lags greater than q. This is a test for an MAQ process. Suppose in an MAQ process, if we plot the autocorrelation function, after some lag, this autocorrelation function will drop down to 0, and that point is the order of the MAQ process. Next point is Rx of M is related by a nonlinear relationship. This is the trouble with the model parameters, B parameters, the relationship is like this. Rx of M is equal to summation Bj plus M sigma V square j going from 0 to q minus m. So, this is the relationship between autocorrelation function and the model parameters. And therefore, model parameters are related with autocorrelation function in a nonlinear manner, and finding out these coefficients by solving nonlinear equations. When suppose data is noisy, this will be a complex problem. Therefore, fitting an MAQ model is difficult. We will give an example, MA2 process. The model is given by Xn, this is the WSS signal, equal to B0 into Vn plus B1 into Vn minus 1 plus B2 into Vn minus 2. Therefore, 2 is the value of Q. So, 3 parameters are there, B0, B1 and B2. Vn can be considered as unit variance white noise, because any variance is there that can be considered in terms of B0. We know the formula for autocorrelation function of a moving average process. So, we will get Rx of 0 is equal to sigma x square is equal to B0 square plus B1 square plus B2 square. Rx of minus 1, that will be also equal to Rx of 1 is equal to, now if we put the formula, our formula here, this formula, if we put that, we will get Rx of 1 is equal to B0 into B1 plus B1 into B2. Similarly, Rx of minus 2 is equal to Rx of 2 is equal to B0 into B2. These are the non-zero autocorrelation values, and Rx of M will be equal to 0 for m greater than 2. The power spectral density will be given by sigma V square into, because this transfer function is B0 plus B1 into e to the power minus j omega plus B2 into e to the power minus j 2 omega mod of that whole square. So, that will be the mod of h omega square. This quantity is the mod of h omega square, mod of h omega square. So, this part is the mod of h omega square, and therefore, this is the expression for the power spectral density of a moving average process of order 2. If we plot this autocorrelation function, we will get a plot like this. Autocorrelation after lag, suppose this is 0, 1 and 2, after that autocorrelation function have become 0. And if we consider the plot of Sx omega versus omega between minus pi and pi, because it is periodic with period 2 pi. So, uniquely defined only between minus pi and pi, and we see that there is a valley portion here. So, that is a characteristic of a moving average spectrum. ACF vanishes after lag 2, PSD shows a valley region. So, this type of, if suppose your observed spectrum has this type of behavior, then we can model it by a MAQ process. So, we discussed about moving average process, and now let us see what is an autoregressive model. Autoregressive ARP, autoregressive model of order P. In this case, the filter defining the random process is an IIR filter and all pole filter, that is important. So, this is the Vn is the white noise and Xn is the WSS process. ARP model is therefore Xn is equal to summation AI x of n minus I going from 1 to p plus Vn. So, this present output, suppose xn, is considered as a linear combination of past outputs plus this is the input term, that is white noise is the input term, and corresponding transfer function is given by 1 by 1 minus summation ai z to the power minus I going from 1 to p. So, this is the transfer function of this IIR filter. Now, in this case it is an IIR filter. So, there are poles, this expression will result in poles. Therefore, this is an all pole model. AIs are to be properly chosen for stability of Hz and hence stationarity of Xn. If Hz is stable, then only this Xn sequence will be stationary. So, therefore, we have to select AIs such that the poles of this filter lies inside the unit circle. So, we have discussed what is an ARP model. Now, let us see what is HCF, autocorrelation function, and PSD of an ARP process. We have to find the HCF, autocorrelation function, and the power spectral density PSD of an ARP process. You know that Rx of m, autocorrelation at lag m, is equal to E of xn into x of n plus m. Now, x of n plus m can be considered in terms of its previous output. That way, x of n plus m we are writing as x of n plus m is equal to summation a I x of n plus m minus I plus v of n plus m, I going from 1 to p. So, this model we are fitting here and then we are taking the expectation inside. So, we will get summation I going from 1 to p of a I into e of x of n plus m minus I, x of n plus m minus I into xn, this xn, plus now next is this term e of v of n plus m into xn. Now, this term, because xn is a WSS process, therefore, this quantity will depend only on the lag n plus m minus I minus n, that will be simply equal to m minus I. So, summation a I into R x m minus I going from 1 to p. So, R x of m is equal to summation a I R x of m minus I going from 1 to p plus, now this quantity expected value of v of n plus m into xn, that will give us this expression sigma v square into delta m. How? Because e of v of n plus m into xn we can write as suppose summation a I x of n minus I going from 1 to p plus v n. Now, these are the past signals and this is the future input. So, they are uncorrelated because this xn is will depend on the previous inputs only, it will not depend on future input. Therefore, this and this expression will be uncorrelated and here Vn and V of n plus m will be uncorrelated, but there will be a finite value, that variance value corresponding to m is equal to 0. Therefore, this expression E of V of n plus m into Vn can be written as sigma V square into delta m, because when m is equal to 0 there will be a value E of V of n plus m, that is E of Vn into Vn, that way sigma V square will come, otherwise it will become 0. Therefore, we have now that Rx of m is equal to summation I going from 1 to p a I Rx of m minus I, all this p previous autocorrelation value plus sigma v square into delta m. This is the equation. This is for all integer values of m. So, that way we get a set of linear equations in terms of the autocorrelation functions. This set of linear equations are known as Yule-Walker equations, and they can be solved to find out the values of AIs. Now, how to find out the power spectral density? Sx omega is equal to sigma v square into mod of h omega square, and if I substitute a mod of h omega square, we will get sigma v square divided by mod of 1 minus summation ai e to the power minus j omega I going from 1 to p whole square, mod of this quantity whole square. So, this is the power spectral density of the ARP process. So, this is the denominator term because it is an all pole filter, these are the filter coefficients. So, that way we will get this expression mod of 1 minus summation ai e to the power minus j omega I going from 1 to p whole square. So, we see what is the autocorrelation function, how they are related with the model parameters, and how power spectral density is related with the model parameters. Fitting an ARP model. Because ARP model is an all pole model, if PSD has sharp peaks, then ARP model will fit it well. Rx of M is related with model parameters in terms of Yule-Walker equation. So, that also we know this is a linear set of equation, therefore, solving this set of equation is easy. Thus, fitting an ARP model is easy. We will consider one example, AR1 process. This difference equation is xn equal to a1 x of n minus 1 plus vn, and corresponding hz will be equal to 1 by 1 minus a1 into z inverse. So, this is a only one pole is there at z is equal to a1. Yule-Walker equation, if we substitute p is equal to 1 in the Yule-Walker equation, we will get the Yule-Walker equation that is Rx of m will be equal to a1 into Rx of m minus 1 plus sigma v square into delta m. We know this expression Rx of m is equal to this. From this my p is 1, therefore, only one term will be there and this term will be there. So, that way Rx of m is equal to a1 times Rx of m minus 1 plus sigma v square into delta m for all m belonging to z set of integers. And Rx of 0, therefore, if we put m is equal to 0, that will be equal to Rx of minus 1 plus sigma v square. And second equation, Rx of 1 is equal to a1 into Rx of 0. That is the when we put m is equal to 1. When m is equal to 0, we get this, but we know that Rx of minus 1 is also equal to Rx of 1. From 1 and 2, we will get a1 is equal to Rx of 1 divided by Rx of 0. This is the value of AR coefficient a1. a1 is equal to Rx of 1 divided by Rx of 0. And we can determine also that relationship, we have to find out what is the variance of the white noise. Suppose that is sigma v square will be equal to sigma x square into 1 minus ai square. So, this is one equation, this is another equation. Two unknowns are there, a1 and sigma v square. So, a1 and sigma v square can be found out from Rx1 and Rx0. So, we have found out what is a1, that is equal to Rx of 1 divided by Rx of 0, and sigma v square, this sigma v square is equal to sigma x square into 1 minus a1 square. After now, we have a difference equation, Rx of m is equal to a1 Rx of m minus 1 plus sigma v square into delta m. This is the difference equation, and I know what is Rx of 0. Rx of 0, suppose it is related with sigma v square, that is this one is Rx of 0, sigma v square is equal to Rx of 0 into 1 minus a square. Therefore, Rx of 0 is equal to sigma v square divided by 1 minus a square, sigma v square divided by 1 minus a1 square. And if I solve this set of difference equation with the initial condition, and we will find out this solution for the autocorrelation function. So, it will be exponentially decreasing function. So, we can plot this autocorrelation function. This is the plot of autocorrelation function for different values of m. So, it will gradually going down, and similarly this power spectral density, in this case pole is at that is real axis, pole is a real number. Therefore, it will have a sharp peak at origin only, 0 frequency only. This is the power spectral density plot of a typical AR1 process, and this is the typical autocorrelation plot. Now, one important interpretation of AR process as the Markov process. Consider the AR1 process, that is xn is equal to a1 x of n minus 1 plus vn. Then probability of xn is equal to x given, suppose x of n minus I is equal to xi, I is equal to 1 to 3 etc. All these are given. Then I know that that is probability of xn is equal to x, that is same as Vn will be equal to, we can write it is equal to Vn, probability of Vn is equal to x minus a1 x1, because when I put x of n minus 1, that will be equal to x1. So, if x of n minus 1 is equal to x1, x of n minus 1 is equal to x1, then what will be Vn? Vn will be xn is equal to x, therefore, Vn will be equal to x minus a1 x1. So, this conditional probability is same as probability of Vn is equal to x minus a1 x1, and the same result we will get if we only consider one term, probability of xn is equal to x, given that x of n minus 1 is equal to x1, then also we will get the same expression. Therefore, this conditional probability given all the previous value is same as the conditional probability given the immediate past, x of n minus 1 is equal to x1. Such a model is known as the Markov model. Thus, AR1 is a Markov model, and this interpretation has wide application. Later on we will see. Let us summarize the lecture. A general ARMA PQ model is mathematically described by a linear constant coefficient difference equation. So, xn is equal to summation I going from 1 to p of ai x of n minus I, plus there will be moving average part summation j going from 1 to q of bj into v of n minus j. This is the general expression for ARMA PQ model, which we derive from the spectral factorization theorem. Then we considered moving average process, which has only numerator part in the filter. So, an MAQ model is given by xn is equal to summation I going from 0 to q bi into v of n minus I. This is the model for the MAQ process, moving average process of order q. The ACF autocorrelation function Rxm of an MAQ process is related by a nonlinear relationship with the model parameters. What are the model parameters? These bi's are the model parameters. They are related with the autocorrelation function. We can find out them from the autocorrelation function, that is Rx of m is given by summation j going from 0 to q minus m bj into bj plus m into sigma v square, where m lies between 0 and q, and Rxm for an MAQ process vanishes after lag Q. Okay, these two factors are important, and this is a nonlinear relationship. Because of that, fitting an MAQ model is difficult. The all-pool model ARP is given by ARP autoregressive process of order P is given by xn is equal to summation I going from 1 to P ai into x of n minus I plus Vn. So, here in the filter model only denominator part will be there. That is why it is an all-pole model. The SCF and the AR parameters, AIs are the AR parameters, autoregression parameters. The SCF and the AR parameters are related by the Ewell-Walker equation. These are the Ewell-Walker equations. Ewell-Walker equations. Because for different values of m, we will get a set of equations which are difference equation in terms of the autocorrelation function. So, that way we will have a number of equations. We can suppose there are p parameters are there, one more parameter is sigma v square. To solve them, we can consider p plus 1 equation out of them, and we can find out those values. And solving those equations are not difficult because they are linear equations. And the PSD is given by this Sx of omega is equal to sigma v square divided by mod of h omega square, that is equal to sigma v square divided by mod of 1 minus summation I going from 1 to P ai into e to the power minus j omega I whole square. Simplest AR model we discussed, that is the AR1 model, which is given by xn is equal to a1 into x of n minus 1 plus Vn, where mod of a1 is equal to is less than 1, that is the requirement for stationarity. AR1 is a Markov process, that also we established. Thank you.